Hello, and welcome to the lecture for Chapter 12 from OpenStax Astronomy. In this lecture, we're going to talk more about the outer planets, the gas giants, that is, and specifically, we're going to talk about those planets' rings, moons, and we're going to throw in something different. We're actually going to talk about the dwarf planet Pluto. To be honest, Pluto could also be included in the next chapter, in Chapter 13, but since it has some moon-like features, we're going to group it in and talk about it here. So, if we're talking about the history of the moons, it all starts with the so-called Galilean moons, which are the four large moons of Jupiter. Jupiter has a lot more than four moons, but it has four very distinctly large moons that are fairly close to the planet. Now, these moons, I said historically, start the discussion of the moons of the outer solar system because they were the first such moons discovered back in the 15th century. Now, what's interesting is they also were used as an argument by Galileo historically to say that the Earth was not the center of the solar system because it showed that other planets had their own moons, thus contradicting the theory that everything must orbit Earth. Well, indeed, these orbit Jupiter in an orbital system. Because one thing that we're going to see throughout this chapter and throughout this lecture is that these planets all have their own orbital systems. These systems all consist of rings. All four of the gas giants have rings, and they all have mini moons, although those moons can be grouped into two categories. Large moons like these, which are large, at least relatively large. We can say more than 1,000 kilometers in the case of some of these moons, many more times than 1,000 kilometers in radius, or even if we're being generous, in diameter. So maybe 500 kilometers as a medium-sized radius moon. But the point is that those moons either be large or medium, so large or medium moons, that are relatively close to the planet, often near the rings of the gas giant of the planet, and perhaps shepherding those rings, and we'll see that. But these moons also have prograde orbits. Okay, so the four moons shown in this image definitely meet that criteria as being large, in this case, moons relatively close with prograde orbits. What's a prograde orbit? Well, it orbits in the direction as seen from above the ecliptic plane of the solar system. That is the direction that all the planets orbit the sun. Okay, it's the same direction that all the planets orbit about their own axes, with the notable exception of Venus, which is upside down, and also the direction that the moon orbits Earth, for example, or the moons of Mars orbit Mars, that is. So that's the dominant orbital direction of the solar system. It's the prograde direction, all right? Because the other moons of all the gas giants, those moons, the further away moons that aren't shown in an image like this, those further away moons all orbit in retrograde orbits, okay? So the mini moons of the outer gas giants, there are also small, distant, retrograde moons. There's still moons of the planet, such as moons of Jupiter, moons of Saturn, and so on, but these small, distant retrograde moons often have irregular shapes. They're not spherical, unlike all the ones shown here, because this image here, figure 12.2, is all large and medium moons. Okay, so the small distant retrograde moons I'm mentioning are in contrast to them, but these get the numbers up to say 60 moons for Jupiter, 70 moons for Saturn, just rough estimates, 30 moons for Uranus, or 27 or something. You know, these maybe another 20 moons for Neptune. Those large numbers of moons, obviously more than are shown in this image, definitely include the small distant retrograde moons. Again, a regular shape for those small distant retrograde moons. Why? Because they're just captured asteroids. Okay, we'll come back to the idea of capturing something when we talk about Triton, a moon of Neptune. But for now, associate it with the small distant retrograde moons, which I'm mentioning now in this part of the lecture, because we're not going to go back to discuss those small moons that much. But they do make up the majority of the moons of the outer solar system. Okay? Captured asteroids, and due to the physics of how they get captured, they end up with that retrograde or backwards orbit. So if, in fact, the process of capturing another body, a chunk of metal or rock that didn't form in orbit around the gas giant, but instead formed separately in the solar system, probably out in the distant Kuiper belt, which we'll talk about in the next chapter. Well, that type of object then, through gravitational attractions, ends up being captured by a gas giant, ends up as a small retrograde, opposite orbiting direction moon. But I do want to briefly mention this image here again, because I went on to talk about the small moons. But this image does show the famous four moons. First one's discovered, Io, looking at Europa. All right. And then we have Ganymede, the largest. The surface looks so similar. And finally, Callisto, the most distant and, well, least interesting of the four, but all large moons. Okay. Ganymede is famous in the solar system for being the only moon that's actually larger than a planet. Ganymede right here, shown in comparison size to our own moon and also in comparison size to Earth, all in the same image. Everything is scaled. Well, Ganymede is actually larger than Mercury. So if Mercury was shown in this image, it'd be slightly smaller than Ganymede. All right. We also see, right, that these moons are stacked up by planet. So the four large moons of Jupiter are shown in the first column. Then we have the large and medium-sized moons of Saturn, the medium-sized moons of Uranus. Uranus does not have a particularly large moon, all right, but it does have these. And by the way, all of these, just to say it one more time, all of these are prograde. These are all moons that orbit in the dominant direction, with one notable exception, which is Triton, which is close in and large, is why it's included here, but this one is retrograde. All right, Triton is the only retrograde large moon, let alone medium moon, in the entire solar system. All right, in the outer solar system. Why is it retrograde? Probably because it was captured, just like all the small ones. It was probably a Pluto-like body, a icy dwarf planet, Kuiper belt object out in the distant solar system, well beyond Neptune's orbit, and got gravitationally interacted with Neptune over a period of time, and maybe with some other interactions with dwarf planets in the distant solar system, and eventually ended up in orbit around Neptune, all right, rather than in a solar orbit. Okay. There is also Pluto. All right, Pluto is a dwarf planet. Pluto has a moon that is fairly large compared to its own size, which we will show coming up. All right, and here's another dwarf planet out in the Eris. So yeah, also out in the solar system. Okay, all right, but anyway, moving on. We're just going to go through fairly quickly and talk about some interesting details of each of the Galilean moons. The Galilean moons are the moons of Jupiter, the big moons of Jupiter. First one's discovered. All right, so least interesting, most distant, just basically an ice moon is Callisto. Callisto does definitely have surface features in terms of almost dune-like features that we see here. It is also fairly heavily cratered. Okay. Then we have Ganymede. Ganymede, largest moon in the solar system, larger than Mercury. Ganymede also has a fairly old surface, which is indicated by the large amount of visible craters on the surface. But there's also some evidence of basically ice flows, cracks in the surface. Ganymede is a mixture of ice and rock throughout its upper layers. Then we move on to Europa. Now, Europa is completely covered in ice. There's strong evidence to support that ice is like a huge floating ice sheet that is above a significant ocean that appears to cover the entire planet, an ocean of water, right? Liquid water. That liquid water is deeper inside the planet, and thus it's warmer, retaining its liquid state. But the surface of Europa is entirely ice. But that ice is very, very active, certainly more active than any features shown on the surfaces of Callisto and Ganymede. The active surface of Europa means that there are few craters because the surface is constantly being refreshed, and we see lots of cracks as ice flows and ice slurries are pushed up to the surface, and viscous, sloshy ice substances are pushed along and flow through cracks and well up out of cracks, all on the surface of Europa, including some geysers. All right, this is a really cool image because we can see a newer crack that cut through from top to bottom, that cut through quite obviously a older, significant cracking surface that itself at some point cut through an even older crack shown over here. Right, so we see it's a continual process, and notice the complete lack of craters. Well, we know that the surface has been refreshed many times since the era of heavy bombardment, the famous first 500 million years of the solar system, and even more recently has covered up any continual craters that have formed since in the last 3 billion years. Finally, moving on to the closest of the moons, because we actually been working inwards towards Jupiter, starting with the most distant moon, Callisto, then moving to Ganymede, Europa, and now finally Io. Well, Io is famous for its volcanoes. It is the most volcanic world. World is a term that includes planets and moons. The most volcanic world in the solar system. Okay, most volcanic, body. Another term for a world. Tons of volcanoes, lots of volcanic flows, lots of eruptions spewing gas and particles and dust, as well as lava flows, dark lava flows. We can see evidence of that throughout this image. If we zoom in, we can actually see an eruption throwing gas high into the thin atmosphere, an atmosphere formed by so much outgassing and so many particles being stirred up, but spewing that out into distant from the planet. The size of some of these eruptions on a planet like Io are best understood by considering its much lower gravity compared to, say, Earth. It is smaller than the moon. The moon has 1/6 the gravity of Earth. We can think of Io as having perhaps 1/8 or 1/9 the gravity of Earth. So that weak gravity means that things can get flung a long way, and these eruptions will push gas and dust particles all the way into orbit around Io, but in a decaying orbit, and they eventually fall back down to the planet. So it's spewing huge distances. Here we can actually see images taken by a Galileo spacecraft, which is a spacecraft named after the famous astronomer, back in the 1990s, showing a point prior to an eruption, the actual eruption taking place in September compared to April, and then coming back a couple of years later, seeing the eruption has died down, but a smaller eruption has begun. 2 small eruptions, in fact, have begun to the side of the original volcano. Okay? There are lava flows on the surface of Io, right, as can be seen in this false color image, right, but still a very high resolution image, showing these just, cracks, almost like the caldera of a volcano here on Earth. All right, and we see sulfur coloring and the yellow coloring covering the surface, a very inhospitable place. But why is Io so volcanically active? And why does Europa have a liquid ocean underneath a very, very cracked and honestly active ice sheet on top? Well, the activity levels of both Io and Europa can best be understood by the topic of tidal friction, because both of these planets, more dramatically Io, are so close to the huge planet Jupiter that they are getting constantly kind of reshifted gravitationally. There's a difference in gravitational pull between different halves of the planet, different depths of the planet due to the planet's own rotation about their axes, and thus that creates tidal friction. Right, in the case of Europa, actual oceans are being pulled by tides. That constant movement creates energy, creates heat within the planet, keeps the planet warmer than it would be if it was not for the gravitational pull of Jupiter, right? That differential pull. And it doesn't show up in a moon that's so distant like Callisto. Very little tidal friction in that case, and less so in Ganymede as well. All right? And in fact, that trend can be shown because we can look at a surface that is constantly renewed for Europa. As we get further out in the Ganymede, we have a surface that does have some features such as ice flows, but still is fairly heavily cratered. And then Callisto is like a dead moon in a sense. No tidal friction means no release of energy that makes its way to the surface of the moon. Okay, now let's go on to Saturn. Okay, so we're done talking about the moons of Jupiter. All right, done talking about Jupiter for now. We're going to now look at a moon, and for some reason, we're looking at an atmosphere. We never discuss atmospheres really in any case for the moons of Jupiter, but here we are, because Titan, quite famous for any moon in the solar system, has a very distinct and dense atmosphere. Okay, now the atmosphere is quite different than an atmosphere like the atmosphere of Earth, and also very different from the incredibly dense atmosphere of Venus, which is high in CO2, or the thin atmosphere of Mars, which is primarily CO2. right? And instead, we have an atmosphere that exists in very cold conditions, because if there's one common theme out here in the distant solar system, is that the radiative energy from the sun is weak, especially going from Jupiter out to Saturn, and then even more so going from Saturn to Uranus to Neptune. We have very, very little light that makes its way from the sun out to that part of the solar system, such a huge distance, okay? But there is the right conditions to have liquid methane on the surface of Titan, a state that would not exist in the inner solar system. Methane is a gas at temperatures in the inner solar system, certainly including temperatures on the surface of Earth. But regardless, we have liquid methane, but enough heat for that methane to go through a cycle where it's warmed up, it's evaporated, it forms clouds. Those clouds then deposit rain, creating an actual methane cycle, just like the water cycle on Earth. Water rising up, clouds drop rain. That rain then flows through rivers, forming lakes, inland lakes, eventually flowing out to seas. All of that happens on Titan, but not with hospitable water, H2O, but instead with the methane, all right? Methane and ethane, right? And we can actually, the upper atmosphere includes photochemical haze, the chemical N2CH4, right? We can see the temperature variation with relatively high temperatures near or in the upper atmosphere, where higher energy photons are being absorbed, and then lower temperatures, but just right for that methane cycle down near the surface, right? Temperatures quite cold, right? Compared to, all of these temperatures are cold compared to, say, 300 Kelvin being a surface temperature on Earth. We can see, right? Because even the hottest part of the atmosphere of Titan is only 180 Kelvin, so very, very cold. All right. Also, notice the pressures only get out to about 1.6 bar. Compare that to Earth, where surface temperatures are around 770 bar. All right. So very different. All right. Here are actual images of the surface of Titan. Here it looks rather rocky. We're not actually seeing that, maybe that rain that we were talking about, that methane rain, but we do see features of definitely swept erosion. There's lots of evidence of erosion, lots of evidence of rocks perhaps that are deposited in flows, shown over here, okay? And here we see, with other images, actual lakes of methane on the surface of Titan. And the color here has to be best understood because the upper atmosphere of Titan is so thick, that thick photochemical haze, that it's actually hard to see through that haze. But in this case, this flyby spacecraft was able to do so, and also able to image those rivers, that part of that methane cycle of flowing liquid methane mixed with ethane. All right. Now moving on to a different moon and a different system, we're going to talk about Triton. Notice that we went from talking about a moon of Saturn, which was Titan, okay, to a moon of Neptune, which is Triton. Two names very similar: Titan for Saturn, Titan because it's such a large moon, it's famous for its atmosphere. Triton associated with Neptune because those are both named after mythology of sea creatures, right? Sea gods and so on. So Neptune and Triton, Saturn and Titan. But also notice we skipped over Uranus, right? We completely skipped over the gas giant Uranus and its moons. Uranus, if you recall from the earlier figure, only has medium-sized moons. Those means moons are very close into the ring, the very faint ring of Uranus, and they're all part of that ring moon system, shepherding the ring and so on. And there's not too much to talk about, right? There's no real specific details that we're going to cover for those moons. But a detail of note that we are going to cover for Triton is that it is unusual because it has a retrograde orbit, so retrograde, but also its surface is quite interesting because we see on its surface not a lot of craters, and we see evidence of basically geyser eruptions that have settled in these big dust rims. I mean, you can actually see that here in the previous image as well, where they stop, right? Because here the South Pole is being slightly warmed by the faint amount of sun energy, creating, or contributing to the energy that takes part in those geysers, those eruptions that are more common in the South Pole at this time in the orbit of the planet and the orbit of Neptune around the sun. And then we can see, surface features like cracks and so on, including some, basically mountains of some sort, as well as very few craters, right? But definitely a surface with lots of features, lots of actual, processes happening. Well, how could that be happening for a moon that's so distant in the solar system? Neptune itself is so far out. What's the energy source? Well, it is best understood by some sort of tidal friction, basically gravitational heating. And because this moon is primarily made of ices of chemicals that would easily be a gas in the inner solar system, like nitrogen and so on, that these hydrogen-based ices, not necessarily H2O ice, they're rather easily melted. So just a little bit of tidal friction goes a long way, making for actually fairly active planets by the standards of, say, a rocky moon like our moon in the inner solar system, which is quite inactive. Okay, and I say planet, I mean world, of course, because in this case, talking about Triton, it's a moon of Neptune. All right, now let's briefly talk about Pluto. Now, Pluto is definitely not a gas giant, and it's definitely not a moon of a gas giant. So its inclusion here is really actually more to compare it to Triton than anything else. Because if we look at Pluto, first of all, we can see why clearly it is not grouped together with planets, certainly not the gas giants, and it's not really in any way comparable to the inner terrestrial planets, because we can see compared to Earth, here is Pluto and its moon Charon. Well, we can see those two moons, or that dwarf planet and its moon, are very small compared to Earth, right? And even small compared to Earth's moon. If Earth's moon was put at the same side-by-side size comparison, it'd be much larger than Pluto, all right? Now, here is the man that discovered Pluto back in 1930, so it wasn't that long ago that Pluto was discovered, and had decades of being considered a planet until eventually it was demoted to be now considered a dwarf planet. But regardless, here's the person who discovered it. Here is the surface of Pluto. Pluto has haze layers, almost a weak atmosphere. It has geysers, like we saw for Triton, moon of Neptune. It has a differential surface, lots of different features, right? Eruptions from those geysers, almost like sheets of ice that exist that seem to melt and refreeze depending on where Pluto is in its orbit and how the tiny variations in energy it receives. That tiny amount of energy, again, going a long way due to the types of ices that exist on the surface of the planet. Okay, the atmosphere is not thought of here. You shouldn't think of the atmosphere as an atmosphere that creates any type of erosion, like the atmosphere we saw for Titan, right, with methane rain and so on. This is a quite different atmosphere. Here, this is atmosphere that is almost just frozen in place. It's almost like a frozen haze on top of the planet. All right, but very, very, very cold, distant world. All right, here's a kind of a false color image of Pluto to highlight the differences in the surface features, the differences in their compositions, chemical compositions showing up as different colors, right? Here's some features, showing, lots of cracks and almost like boulder shapes that perhaps have been broken up and risen to the surface, and then create a shore on a huge sea of frozen nitrogen. All right, quite amazing surface features here. Okay, here's looking at more of those surface features of Pluto, and now looking at the moon Charon. All right, so if we look at Charon has almost a rockier surface, less activity, but it is significantly smaller than Pluto. All right, so less tidal friction there, because the size does help contribute to some warming and melting within, and that heat rising to the surface, but not happening so much here on Charon. But one thing I do want to mention about Charon and Pluto together is their orbit, because Charon and Pluto have a double tidal locking in their orbit. So double tidal locking. Okay, or you could say that their orbit is locked as a double tidal orbit, or a double tidal locked orbit. Okay, so what does that mean? Double tidal locked. Well, if you recall, our own moon has an orbit here, almost a scale in size, has an orbit around Earth where it is tidally locked to us. So the moon is tidally locked to Earth, but not the other way around. Well, in the case of Pluto, it is the other way around. Both planets are locked to the other. What does that mean? Well, tidal locking refers to always having one face of a world face another. The moon has one side that always faces us because its orbital period matches around its own axis. All right, okay, we'll say it this way. Its orbital period around Earth matches its rotational period around its own axis. So another way to say it, the day length of the moon is the same as the orbital period of the moon. Well, here with Charon and Pluto, they both orbit around a center of mass point because they are so comparable in size. That center of mass is actually not within Pluto itself. So you can think of them orbiting around a shared point, but much closer to the more massive Pluto, that center of the system. But also they orbit in a way where Pluto always has one face facing Charon. Charon always has one face facing Pluto. So that means that on one side of Pluto, a far side of Pluto, you would never see the moon Charon. On the other side of Pluto, the moon Charon would just sit in the sky. It wouldn't rise or set. It's always at the same fixed point in the local sky on the side of Pluto that can see Charon. Likewise, on the surface of Charon, there's one side of Charon where you can see Pluto, and another side, so almost a dark side of sorts, that is constantly orbiting around Charon with always facing away from Pluto, so you would never see Pluto. Okay, so both planets have sides that always face the other, and another side that faces away. That's what double tidal locking is. That's a process that any two-body system like the moon and Earth approach over time. It's certainly theorized that Pluto and Charon were not always in a double tidal locked orbit, but over millions and billions of years fell into that orbit or approached that orbit. It's a final state of bodies. Eventually, the moon and Earth would approach that type of orbit over billions of years, but by that point, the sun will have, will no longer be around. It would take too long, the process for the double tidal locking between the Earth and the moon. But it is the process that the Earth and the moon are slowly approaching. Essentially, the Earth is slowing down in its rotation around its own axis, and the distance between the moon and Earth is growing, which is slowing the velocity of the moon. So eventually, those two will match up, and the length of one day of Earth will match the length of 1 month of orbit of the moon around Earth. All right, so we would have a much longer day in billions of years. Okay, and that does currently happen with Pluto and Charon. All right, so we were looking at the moon Charon. Now let's quickly wrap things up with reflecting back on the ring systems. All right, this is just highlighting the fact that all four of the gas giants, Jupiter, Saturn, Uranus, and Neptune, all have rings. Now the only bright, reflective, high albedo rings are those of Saturn. The other rings are darker, less reflective, thus very hard to see in the visual spectrum. Maybe sometimes easier to see with actual infrared images because they do still have release some heat. But regardless, very faint dark rings. Jupiter does have a very large inner ring. All right. Obviously, Saturn has its huge bands of bright rings. All right. Uranus has very faint and very, very thin bands of rings. Uranus has some thin bands of rings as well as one thicker band. What is this tidal stability limit? Well, it's a relative distance from the planets. That is because the scale, by the way, is different in each row. So this is scaled, these images, so that this tidal stability limit creates one vertical line here, as we can see. Well, that tidal stability limit in actual kilometers is different for each planet. It's dependent on the mass of the planet. Jupiter has a much further out tidal stability limit than, say, Saturn and Uranus. But if we scale the image for all of them and line it up, then we can see its common phenomenon. Because what does it represent? The tidal stability limit, it represents the point where a moon gets torn apart due to tidal friction. So any moon that exists within that tidal stability limit will not last forever. It will slowly get torn apart by the gas giant. Okay, because just the tidal friction is so great. Basically, the pull on one side of the moon is larger than the pull on the distant side, and that just starts tearing the moon apart. All right, it's a gradual process. It can take tens or hundreds of millions of years, but it does gradually happen. This right here, which is pretty cool, you can actually see Io is shown to scale as the largest moon or basically not the largest, because here we have actually Titan, which is also quite close, relatively close to the tidal stability limit. But that moon is shown, right? Io is shown clearly very close in, thus explaining its huge amount of heat, why it's so volcanically active, because it's almost close enough to get torn apart by Jupiter. All right. Notice that the other Galilean moons, namely Europa, Ganymede, they're not even shown in the scaled image because they're so far out, right? At least relatively far. All right. We do see that many moons do exist within the tidal stability limit. Certainly in the case of Uranus, we have some relatively large, medium-sized prograde moons. Well, those are eventually going to get torn apart. For now, they're shepherding. They're said to shepherding the rings, which means that they're actually creating bands within the rings because their gravitational pull is affecting the rings. But regardless, they're in an unstable state. Uranus does have other small or medium-sized prograde moons. Also to note, all of these moons in this image, represented by the little black dots, all of these are prograde, because the only, medium-sized retrograde moon, orbiting the opposite direction is that of Neptune, being Triton. Well, Triton is not shown because Triton is relatively far from Neptune, so it's actually does not show up in this image. All right. So looking at the beautiful striking rings of Saturn, all right, looking at an artist's version of the clumps of ice, so highly reflective ice that make up the rings of Saturn. The clumps come in sizes that kind of match up with common sports balls, such as baseballs and basketballs. So you can imagine that's the size of individual clumps, trillions upon trillions of them, okay? And now we're going to take a quick detour to talk about a moon that has just become famous and well known in the last decade or so, and that's the moon Enceladus. Now, Enceladus is like a little Europa. It has a lot of features very similar to Jupiter's moon Europa, but Enceladus is not a moon of Jupiter. It instead is a moon of Saturn. But the reason it has become so interesting to scientists is a recent flyby by the Cassini spacecraft shows that there are large geysers on the surface of Enceladus. Now, Enceladus has a surface that is icy, very little cratering, lots of cracks on that surface. Now, some cratering, as you can see, but lots of renewing cracks. And that's because, just like Europa, Enceladus is thought to have a almost world-covering ocean, liquid water ocean, H2O, beneath the icy surface, okay? Now, that water is obviously warm enough to push up to the surface along these warmer cracks that especially exist near that one pole that is shown in the image, and that those geysers push up through them, creating large geyser points as well as long streaks of geysers along the cracks, okay? Now, back to the rings. We have the rings of Uranus, very faint, imaged in this long exposure image, all right? And the even fainter rings of Neptune out in the dark part of the solar system. This is basically glare over here that is happening because the planet is so bright, but we're trying to resolve in this image taken way back by Voyager 2. We're trying to resolve the actual faint rings, all right? Here we can actually see some rings of Saturn and the shepherd moons that are included within that ring system, those moons that eventually will get torn apart, right? Many of those shepherd moons are actually appear to be captured asteroids themselves with irregular shapes, okay? Here we can see that a shepherd moon is creating these odd ripples or perturbations in the ring, okay, because there's a gravitational interaction between them, as well as gravitational interactions within those ball-sized particles within the ring itself, so quite complicated phenomenon. All right, and that concludes our lecture on the moons and rings of the gas giants and Pluto. Thank you so much for watching. I hope this lecture has been helpful and interesting.